In our quest to classify all thermodynamic variables and seek an overarching structure to the system, we're first going to distinguish what is a thermodynamic potential from what is not. We have a great example of a thermodynamic potential already. It's the internal energy. And let's start with the internal energy and just recall some of its properties. It obeys what we call the fundamental thermodynamic identity. The du is equal to TdS minus PdV plus mu dn. This means that the internal energy as a function has a special relationship to entropy, volume, and particle number. If we think of these as variables in a exact differential scheme, the ds, dv, and dn are the independent coordinates of a space where internal energy is the function that underlies them. This special relationship means that the derivatives of internal energy with respect to those quantities have a very simple form. du over ds, while holding n and v constant, is equal to t. du over dv, while holding entropy and number of particles constant, is equal to minus p. And du dn, while holding the entropy and volume constant, is equal to the chemical potential. These derivatives always give us the conjugate variable to the independent coordinate. Temperature and entropy are conjugate variables, pressure and volume are conjugate variables, and chemical potential and particle number are conjugate variables. So when we take this derivative, with respect to s, we get t, with respect to v, we get p, more or less with a minus sign, and with respect to n, we get mu. So it's clear that the internal energy, if we think of it as a function, prefers to be written out in terms of entropy, volume, and particle number. Those are the three variables where the derivatives will have the simplest answers. As we know from our work on exact differentials, if we were to take this derivative, say, du dv, and hold temperature constant instead of entropy, we definitely wouldn't get the pressure. We would get something totally different. The fact that internal energy prefers to be expressed in terms of these three variables leads us to call those the natural variables for internal energy and gives us the concept of natural variables for a given thermodynamic potential at all. So for U, the natural variables are S, V, and N. And that's what we want to say about the internal energy for now. We've actually discussed a second thermodynamic potential. I didn't say it was one at the time, but see if you can guess which one it is. If you guessed enthalpy, you would be correct. Let's recall a bit about the enthalpy. It's directly related to the internal energy, only different by an addition of the product PV. So the enthalpy also has units of energy. And if we recall the lecture on enthalpy, we should remember that it has derivatives that give us specific other quantities. When we worked out the differential of H with the plugging in the fundamental thermodynamic identity and doing the product rule here, we got TdS plus VdP plus mu dn. This immediately indicates to us that the enthalpy prefers to be expressed in terms of entropy, pressure, and particle number. So the natural variables of the enthalpy are S, P, and N. And find that if we take derivatives of the enthalpy with respect to these quantities, we will get the conjugate variables, dH, ds, while holding pressure and particle number constant gives us the temperature. dH dP, while holding entropy and particle number constants gives us the volume. And dH dN, while holding entropy and pressure constant, gives us the chemical potential. So these derivatives look similar to the ones for the internal energy. It's not by mistake, but they have some things in different places. In the derivatives, we are now holding pressure constant instead of volume, or using pressure as our variable instead of volume. And in our derivatives, we get T and mu for these. These look almost the same, but the derivative with respect to pressure now gives us the positive volume of the system. So the similarity between the internal energy and the enthalpy is not accidental. What we've done here essentially is we've done a change of variables from treating volume as the independent variable to treating pressure as the independent variable. And the way that we accomplish that is by adding the term PV, the product of these two conjugate variables, to the internal energy. Enthalpy still depends on entropy and particle number, though. We've just made a change from volume to pressure. So let's keep track. U is a function, most naturally, of S, V, and N. H is most naturally written as a function of S, P, and N. So we now have two thermodynamic potentials and a way to switch between them to possibly arrange our formulas for derivatives in a more convenient form. So our natural question here is, if we look at what's happened here, is there any way to change to a new thermodynamic potential whose natural variables are even different from S, V, and N, or S, P, and N? Perhaps we'd like to find a potential whose natural variables are temperature, volume, and particle number, instead of using entropy. Indeed, that type of potential exists. And we can obtain it by a similar way from how we obtained the enthalpy. To get to the enthalpy from the internal energy, we added pressure times volume. And that had a cancellation occur that eliminated the PdV terms and gave us VdP. If we want to eliminate the TdS term in favor of SdT, we need to add on or subtract a term that is equal to the product of temperature and entropy. U minus Ts should do the job. And we call this thermodynamic potential the Helmholtz free energy. Now, we may have more conclusions about this type of energy in the future, but for now, we can just appreciate that this is another thermodynamic potential, and it's going to have different natural variables and different derivative formulas. The name is some person, and the free energy portion is just, again, a name. It doesn't mean that this energy is any more special than any other type of energy. Let's work out explicitly the Helmholtz free energy differential using the fundamental thermodynamic identity combined with the product rule. I'm substituting in the fundamental thermodynamic identity And continuing to write the product rule here. And the cancellation that we are looking for indeed does happen. We've got a TDS term there and a TDS term there that go away. So our expression for dF simplifies to minus S dt minus P dV plus mu dN. This is the fundamental thermodynamic identity expressed in terms of the Helmholtz free energy instead of the internal energy. From this version of the thermodynamic identity, we can immediately write down what the derivatives of the Helmholtz free energy should be. We just have to look at which terms are the differentials. dF dt, while holding volume and number of particles constant, shall give us the opposite of the entropy. dF dV, while holding temperature and number of particles constant, will give us the opposite of the pressure. And dF dN, while holding temperature and volume constant, will give us the chemical potential. So those three derivative relationships are, again, particularly simple, and they indicate now that the Helmholtz free energy is most naturally expressed in terms of temperature, volume, and particle number. There's one more type of free energy which we will see in common use. And this free energy is designed with the goal of switching our independent variables from SVN all the way down to temperature, pressure, and particle number. So to do that, we have to first do what we did for the enthalpy. Add PV to the internal energy. And also do what we did for the Helmholtz free energy. Subtract TS. This is another thermodynamic potential. It's called the Gibbs free energy. Of course, Mr. Gibbs did wondrous things for the study of thermodynamics, so he rightly deserves his name to be assigned to one of these quantities. But again, it's just a name. Just because it's called free energy, it doesn't necessarily mean that it's more important than any other type of energy. It just will have different natural variables that might be useful or less useful in a given situation. Let's calculate the differential explicitly of the Gibbs free energy. Since we've subtracted and added two things here, there's a number of additional terms, but we still get cancellations. The PdV cancels, and the TDS cancels. So we're always left with three. We have minus SDT plus VdP plus mu dN. This is the fundamental thermodynamic identity expressed in terms of the Gibbs free energy. Let's write out the derivatives. At this point, we should be able to almost guess what they are without talking. Our natural variables are temperature, pressure, and particle number. These derivatives have simple forms. They give the conjugate variables with a positive or negative sign. So clearly, the preferred variables in which to express the Gibbs free energy are temperature, pressure, and particle number. Notice that each time we made one of these transformations, we eliminated an extensive variable in favor of an intensive variable, going from volume to pressure, going from entropy to temperature. The Gibbs free energy is expressed in terms of two intensive variables and one extensive variable. The only extensive variable is the number of particles, capital N. So the Gibbs free energy is favored by people who work at constant pressure and constant temperature situations. Most of us live at constant temperature and constant pressure, and most chemistry happens at constant pressure and constant temperature. So we'll find in the future that the Gibbs free energy is a very convenient one to use for situations of chemical reactions. There is another aspect to these thermodynamic potentials, which comes from looking at what their Euler integral forms would be. Remember, the Euler integral form for the internal energy was Ts minus PV plus mu n. To transform from internal energy to enthalpy, we added PV. If we add PV to the Euler integral form for the internal energy, it simply cancels the minus PV term. And we find that the enthalpy has an integral form that is equal to temperature times entropy plus chemical potential times particle number. Similar comments to this Euler integral form apply to the one for internal energy. It's a nice equation that relates things we might not have expected, but to use it, we pretty much have to know all of the state variables ahead of time. For the Helmholtz free energy, when we subtract Ts, it removes this term, minus PV, plus mu n is all that's left over. And when we calculated the Gibbs free energy, we added PV and subtracted Ts. So the only thing that's left over is mu n. So the Gibbs free energy simplifies quite drastically in terms of its integral form. It's equal actually to the chemical potential times the particle number. Notice that the particle number is the only extensive variable in the Gibbs free energy. So if we were to write the Gibbs free energy as T, P, and N equals to mu times N, the chemical potential would therefore need to be expressed in terms of temperature, pressure, and particle number. But if we look at the scaling relationship of this equation, a thermodynamic potential is extensive, so G will scale up. And the particle number is extensive, so the particle number will scale up as well. So in order to satisfy the scaling behavior required of extensive variables, these two can cancel, but the chemical potential has a scaling factor sitting in its potential dependence on particle number. What we can glean from this fact is that the chemical potential cannot depend on the particle number at all. It can only, if it's if the chemical potential is written as a function of temperature, pressure, and particle number, the dependence on the particle number will cancel out completely. Therefore, the Gibbs free energy divided by the particle number is equal to the chemical potential when expressed in terms of temperature and pressure. This is another reason why we find the Gibbs free energy appearing all the time in chemistry. The chemical potential is what controls chemical reactions, and the Gibbs free energy is essentially the chemical potential. We can derive actually a very powerful relationship between thermodynamic quantities, in addition to all the thermodynamic potentials we just discussed, by doing something that seems like it almost ought to be not allowed. Let's define a thermodynamic potential called the zero. It is equal to U minus Ts plus PV minus mu n. It's almost like we want to transform all of our variables to intensive ones. So we do the thing for Helmholtz, we do the thing for enthalpy, and why not just add on a term to change from n to mu. Of course, based on the Euler integral form, this will just be equal to 0. But let's go through the calculation of its differential just to see what happens. Clearly, if we take the differential of 0 on the left, we still get 0. The differential of U will be from the fundamental thermodynamic identity. TdS minus PdV plus mu dn. The other terms all have product rules, so it will amount to 6 pieces. I'll write those all out quickly. So we're left with 9 terms. But again, 3 of them cancel. So we have 0 equal to minus SDT plus VdP minus n d mu. So 0 is an energy value, and it actually acts as a potential as well. There's not really anything to calculate, though, so we don't call it a thermodynamic potential. Instead, we talk about this equation as itself. This equation we call the Gibbsduhem equation. And notice that the differentials are all on the intensive variables. The Gibbsduhem equation is a fundamental relationship between intensive variables in a one-component system. Sometimes we see the Gibbs-Duhem equation solved for a particular variable. Let's look at it for pressure. If we move pressure to the other side, we'll obtain VdP equals SDT plus n d mu. And what this means is that the pressure, if we divide both sides by volume, the pressure can in some way be thought of as a thermodynamic potential with independent variables of temperature and chemical potential. If we express the pressure in terms of temperature and chemical potential, it will not involve any extensive quantities at all. If we take the derivative of that expression, dp dt, with respect to mu, we will get the entropy per volume. And if we take the derivative of pressure with respect to chemical potential, while holding temperature constant, we will get the number of particles per volume, or the number density. The Gibbs-Duhem equation can be solved for other variables, such as solving for t, and used to set up other derivatives, but they are all similar to these ones. What it tells us is that a ratio of 2 intensive variables will be related to somewhat its conjugate density. Pressure over temperature gives us entropy over volume. finally, what we can say from the Gibbs-Duhem equation is that if we take any intensive variable, chemical potential, pressure, temperature, I want to write this as T is expressed as T of P and mu, or it turns out any other intensive variable in a one-component system. Let's define the entropy per particle number, lowercase s, and I'll write lowercase s in terms of temperature and pressure. Any intensive variable written in terms of two other intensive variables will involve no other variables in its formula. Any intensive variable can be expressed in terms of, at most, two other intensive variables in a one-component system. It means that if we know the temperature and the pressure of our one-component system, there's nothing else to know except its overall size and scale. If we know the temperature and pressure, the chemical potential, the entropy per particle, the density, all of these things are completely determined by just those two numbers. If we want an extensive quantity, we just take an intensive density and multiply it by some scaling factor for the size of the system. This seems like quite a bold claim. Let's test it out for some of our quantities and equations for specific systems. I'm trying to write out our old friend, the Sackur-Tetrode equation. It's a great example of a complicated equation that looks like it's got a lot of stuff going on. But if we look at it in terms of intensive variables, it's actually quite simple. A ratio of S to N would be intensive. A ratio of volume to number of particles would be intensive. And a ratio of internal energy to particle number would be intensive as well. But we still have to address this claim that if I took the time to express this, say, in terms of only temperature and pressure, that no N's, no U's, no V's would appear. They would all somehow find a way to cancel out. And let's see if that happens. S over N is equal to K times the natural log. I want to eliminate everything I can in favor of temperature and pressure. So let's look at volume. We've done the derivatives of this. We know that in this ideal gas system, the volume can be expressed as nkt over P. So we'll do that. V over N is equal to KT over P. We also know that the internal energy is 3/2 nkt. So let's use that here. 4 pi times m times KT, the n's will cancel, the 3 will cancel, and the 2 will cancel with the 4. So I'll have 2 pi mkt over h squared, 3/2 power, plus 5/2 outside. Well, there you have it. On the right side, we have only reduced to dependent on temperature, pressure, and other pure constants. And on the left side is our intensive variable. So it doesn't matter what thermodynamic model you're working with, actually, ideal gas, Einstein solid, two-state system, or something that you just made up. If it has a thermodynamic potential that describes it, that has the correct scaling behavior, if you write out, say, anything arbitrary, the density, in terms of the chemical potential and the entropy per particle, those two, when plugged in, will result in something that depends on no other variables, only those two that you've chosen. So let's summarize the 4 thermodynamic potentials we've discovered and the Gibbs-Duhem equation. We have U, internal energy, all of its derivatives can be summarized by the fundamental thermodynamic identity. Its natural variables also appear as the quantities with differentials in this thermodynamic identity. Sorry, TDS. Better get it right. And its Euler integral form is U equals TS minus PV plus mu n. The enthalpy remains the same except for the switch to pressure plus VdP, and is equal to TS plus mu n. The Helmholtz free energy F switches the temperature as its natural variable, but stays with volume and particle number. Its Euler integral form is minus PV plus mu n. And finally, the Gibbs free energy changes totally to intensive variables except for particle number. And its Euler integral form is very simple, just mu n. Finally, we have the Gibbs-Duhem equation, where 0 is equal to SDT plus VdP minus nd mu. It should be a minus here, here, and here. That is correct. So this is our summary of the thermodynamic potentials. There's 4 of them that we should know about in the scope of this course. They are all energies. They all represent some type of energy quantity, and their derivatives give us the state variables. Temperature and entropy are conjugates, pressure and volume are conjugates, chemical potentials and particle number are conjugates. And finally, if we eliminate all of the potentials from the derivative identity, we get only intensive differentials, and we get what's called the Gibbs-Duhem equation. That is a fundamental relationship between the intensive variables alone in a one-component system.